Here we're going to talk about Newton's third law, but let's review friction a little bit before we do. We've got a book that has a weight of 20 newtons and it's sliding across a table. If a vertical force of 10 newtons down is being applied to the book as it's sliding, the magnitude of the normal force acting on the book will be, well, we know the weight of the book is 20 newtons. So there's our weight, 20 newtons. The normal force must be acting upward, assuming that the table is horizontal. So there's our normal force. And an additional vertical force of 10 newtons down is being applied to the book. So 10 newtons. So there's our additional applied force downward. And we assume that the book is not accelerating up, and it's also not accelerating downward, which means that the forces must be balanced on the book. So the normal force must be equivalent in magnitude to the combination of the two forces here, the applied force plus the weight. So we get 30 newtons for the magnitude of the normal force. If the coefficient of friction between the book and the table is 0.3, the magnitude of the frictional force will be, well, friction force is equal to the coefficient of friction times the normal force, which in this case then would be 0.3 times 30 newtons. So we get 9 newtons for the magnitude of the friction force. All right, Newton's third law. We've talked about Newton's first and second laws. Obviously, this one comes next. And it's a law that you've had some experience with, but you perhaps just didn't realize it. This is an expression for Newton's third law you may have heard before. For every action, there's an equal and opposite reaction. This is an expression that is sometimes used in conversation, but not necessarily in the context of physics. And here, really, we're talking about force, not surprisingly, because Newton's laws really are all about forces acting on objects. This is a better way to describe Newton's third law. For every action force on object B due to object A, there is a reaction force equal in magnitude but opposite in direction on object A due to object B. So there are a couple of key things here. I've underlined object B and object A. It's very important to realize that Newton's third law is about forces that act on two different objects. We often say that no force acts alone because every force has a corresponding reaction force. So those are very important terms as well. Action force and reaction force. Let's look at some examples. An object near the Earth's surface experiences a gravitational force of 15 newtons down. What's the reaction force? Well, here the two objects in question are the object with the gravitational force acting on it and the Earth. So the Earth experiences a gravitational force of 15 newtons up. So the object experiences a gravitational force from the Earth pulling down, and the Earth experiences a gravitational force of 15 newtons up exerted by the object. If we have the same object resting on a table experiencing a normal force of 15 newtons up, what's the reaction force? Here we have the object on the table and the other object is the table. So the reaction force is the 15 Newton normal force downward that acts on the table. A person with a mass of 55 kilograms is standing on a frictionless ice rink, and they throw a 5-kilogram ball with a force of 25 newtons east. What is the acceleration of the ball, and what is the acceleration of the person? We can think of this as kind of like a human rocket. This is how a rocket works. A rocket pushes material usually backwards, and usually that material is fast-moving gas of some sort, and then the reaction force of the that expelled material, called the propellant, acting on the rocket body itself, is what propels the rocket forward. Here, the propellant is the ball, and the rocket is the person. Well, let's have a look at the acceleration of the ball first. We've got the force acting on the ball, 25 newtons east, and we'll divide by the mass of the ball. So here we're using Newton's second law. So there's the formula for Newton's second law. And we're using the given force, 25 newtons east, on the ball. So we get 5.0 meters per second squared east for the ball's acceleration. For the person, you'll notice that the magnitude of the force we use is the same, except that the direction is different. So the reaction force is the force that the ball exerts on the person. So instead of being to the east, now the force is to the west. The person's mass is considerably greater than the mass of the ball, so the acceleration turns out to be lower for the person. And their acceleration is to the west. Two boxes with masses of 45 kilograms and 15 kilograms are side by side on a frictionless surface. A horizontal force of 48 newtons is applied to the 45 kilogram box to move both boxes. Determine the magnitude of the force the 15 kilogram box exerts on the 45 kilogram box. So here's a diagram to show the system. So we could call this a system diagram. It's not just a free body diagram because it shows all the objects that are acted upon, all the objects connected in this case. We can see the applied force of 48 newtons that's being exerted on the 45 kilogram box. Now we're going to determine the magnitude of the acceleration of the system. So we'll write down our given values and our unknown value. In this case, our unknown is the acceleration. Then we'll our equation and solve. So we have 48 newtons using the applied force, which of course becomes the net force in the horizontal or x direction because it's a frictionless surface. So there are no other forces in the horizontal direction. Notice that we've used the entire mass because both boxes are accelerating together as one large mass. And we get a magnitude of 0.8 meters per second squared for the acceleration of the entire system. Now we're going to look at the net force only on the 15 kilogram box. We'll use Newton's second law again, but our given value for mass is a little bit different. Our acceleration is known now from the first part. So our unknown in this case is the net force, but only on the 15 kilogram box. So we select our equation and we multiply and we get a net force of 12 newtons acting on the 15 kilogram box. And that net force has to be due to the force of the 45 kilogram box pushing on the 15 kilogram box. There are no other horizontal forces acting on the 15 kilogram box. Now Newton's third law can be used. The force of the 15 kilogram box acting on the 45 kilogram box has to be the same in size, or has to have the same magnitude as the force of the 45 kilogram box acting on the 15 kilogram box. 12 newtons. So both of those forces have the same magnitude or size, but they have opposite directions. Now we'll try an inquiry activity with Newton's third law, and we'll try a little bit of practice as well.